Okay, class, we've reached the section that I've dreaded. This is not something I feel so comfortable about going over. There are much better mathematical minds out there than my own. So if you want a really good primer on the Lorentz transform, I will provide those links on Blackboard. But in any case, I need to go through this section, and I'm going to try to do my best as I go through it. And if I'm a little bit clumsy, please excuse me. So here we go. I'm going to try my best. Now, I've already talked about the Galilean transformation. Basically, when we go from one frame to another frame, all we really have to consider is the movement of the one frame compared to the other. Normally, we line up the movement. In this case, I've lined up the movement in the x direction so that when I want to transform my coordinates from one frame to a frame moving with respect to that, I only have to change my x coordinates. So there you can see the difference between my primed or moving frame of reference compared to my original inertial frame of reference. Again, all the other coordinates are unchanged, y and z, which are perpendicular to the direction of movement. No change there. And time is pretty much just held as absolute. If we look at the Galilean transformation, and we look at it in sort of a two-dimensional representation, now we're going to go into an area where we're going to include time with the three spatial dimensions. So we're really talking about 4 dimensions. So I'm trying to take something that's 4-dimensional and project it onto a 2-dimensional surface. It's okay. Y and Z don't change, so we're perfectly fine there. But you can see from one frame of reference to the other frame of reference that there is that offset due to the velocity times time. And of course, there's no change to our time axis. So here, time is represented in the vertical axis. We have space, or one of the spatial dimensions, represented in the horizontal direction. And from this point on, we are going to try to, have everything have the same dimensions. So I'm going to take time and multiply that by the speed of light. Okay, and what that it does a number of different things, but one of the things that it does is it makes them dimensionally equivalent. X is in meters. Time now becomes meters per second times seconds, and that gives us back meters. So here's our Lorentz transformation. And with the Lorentz transformation, it is a linear transformation. So we are going to map from one set of coordinates to another set of coordinates. And the Lorentz transformation allows us to do this, to go from our initial frame of reference to another frame of reference moving with respect to it. And in this case, we see that things are a little bit different. Before, the only thing that really changed was x in the direction of movement. Y and Z also, remain unchanged in this type of transformation. And we, of course, have time, which is no longer absolute. And of course, we've already discussed the fact that we get, spatially, we get length contractions, and for time, we get time dilation as we transform from one frame of reference to the other. Again, I'm sort of a little clumsy with the way I'm presenting this, but that's what we can definitely observe here with this transformation. We can see where the length contractions and the time dilations come from in this. Now, let's go back to our 2-dimensional representation of a 4-dimensional situation. It's hard enough to represent 3 dimensions in 2 dimensions. Now we're trying to do the same with 4. Okay. Again, for position at least, we can say that the y and the z direction don't change. So I don't have to be too concerned about that. But notice what happens. Now, before, our vertical axis sort of moved, I'm mirrored here, sort of moved over, if you will. There's almost like a shearing effect that took place as we transformed from one to the other. Now you can see that not only is our vertical axis beginning to rotate in this direction, our horizontal axis is also rotating the other direction. So as you go faster and faster, it's the Lorentz transformation almost makes these two axes converge to a 45-degree angle, which represents as a velocity approaches the speed of light, both of these begin to collapse on that 45-degree angle. And again, that's why I chose, well, that's why they choose C times T, because in this, traveling at the speed of light would correspond to a 45-degree angle. Again, a little bit clumsy on my part. So here is what our Lorentz transformation looks like, going from the white grid, which is our unprimed frame, to the yellow grid, which is our new coordinate system. But again, you have to remember that this is a two-dimensional representation of actually 4 different dimensions, where time is one of the other dimensions. And this, I think in classical physics, we always say, well, it's a scalar or a vector. Time is a scalar, displacement is a vector. And now we're almost treating time as being a vector. Okay, so when we talked about simultaneity, we used the example of the boxcar getting hit in the front and the back of the car, okay, by lightning. According to one observer, this happened simultaneously. The observer on the ground in the frame, which, from our perspective, we held not moving. You can see that these two events, yes, they would occur on the same timeline according to that observer on the ground. But now when we transform to the observer who's moving, this is a little bit backwards, I know. We see that with this type of transformation, the green point and the red point no longer are on the same timeline, okay? Now, what's happened here is the red timeline, or the red point's timeline, is represented by this thicker yellow line right here. And we actually have to go forward in time. We actually have to go up in time, okay, before we reach this green right here. And, past is down, future is forward or upward. You can clearly see that in this type of representation, that red happened before green, which is exactly what happened with our boxcar. So, the Lorentz transformation, when we do it visually like this, it actually makes it a little more clear, why events aren't necessarily simultaneous. Again, this is just looking at it without so many grid lines. Once again, according to one frame of reference, both green and red happen at the same time. They're different places, but they happen at the same time. And then as we make this transformation, clearly, events that are happening at the same time as green would occur here for red's location. So red happened already. Green then happens on a different time. Now, here is what the Lorentz transformation matrix looks like. If you've taken linear algebra, you're well aware of what a linear transformation is. And basically what we have is a vector with 4 elements. We sometimes refer to this as a 4-vector, just to emphasize the fact that we're including this extra element to it. We're including this extra dimension to it, which is the speed of light times time, that time dimension right here. So again, it's viewing everything in terms of space-time, 4-dimensional. And as we transform from our one frame to another, we can use this matrix. This matrix basically represents our transformation. We can use this matrix in order to map from one place to another. Again, here's gamma. We're familiar with gamma already. We've used that with length contraction. We've used that for time dilation. If we want time dilation, we want to go from one frame to another. We typically, to show the dilation, we multiply the change in time by gamma. Time gets longer. If we want to do length contraction, then we typically will divide by gamma. Beta is just, again, to make things a little bit easier to see. Beta is just the ratio of V to C. It's the fraction of the speed of light that we're traveling between one frame and the other. And again, we might represent this 4-vector. There's so many symbols that I've seen for the 4 vectors. Sometimes, you'll see it represented with superscripts. I'm just using this representation right here, where I'm using capital R as opposed to small r, lowercase r. Lowercase r would be our x, y, z vector, our 3-dimensional vector x, y, z. Here, we're going to one more dimension, and we're including CT here. So, basically, this linear equation would be represented like this. Here's our 4-vector. We multiply it by the Lorentz transform matrix. Or I should say, here's our original 4-vector. We multiply it by the Lorentz transform matrix, and we get our new coordinates. Now, what's interesting is, and I didn't do a great job illustrating this, but bear with me. Imagine that we do some type of rotation. Okay, we do some type of rotation with our coordinate system. We know that if this is our normal 3-dimensional vector, and we rotate our coordinate system, that type of transformation does not change the magnitude of the vector. Basically, r squared, we still have the same length. All we've done is rotated everything. So during a normal rotation in 3 dimensions, the magnitude of all our vectors remain constant, invariant. Okay. For our 4-vector, okay, it's not a circular rotation in the traditional sense. Clearly what you see taking place here is both our x and our t-axis being rotated. Okay, sometimes this is referred to as a hyperbolic rotation, but that's a little beyond my my expertise and ability. Since this is an introductory course, I'm going to basically just say, I'll leave that one alone. But again, when we do this transformation, although it isn't a circular rotation in the traditional sense that we have with a 3-dimensional vector, there is this quantity s which is invariant, where just intuitively, if I were to take the length of a 4-dimensional vector, it would be x squared plus y squared plus z squared plus ct squared. But notice I have a negative sign right here. Again, this is sometimes referred to as a hyperbolic rotation rather than a circular rotation. But this remains constant. This value S remains constant under this transform. Okay, sometimes you'll see these light cones represent different events or sequence of events. And here, what do we have here? We have 4 dimensions that we're trying to represent 3-dimensionally, but projecting it on a 2-dimensional surface. So again, I do my best when I try to draw these out to best represent what's going on. Okay, so in any case, let me just move this up here. We have these 45-degree lines, which represent the speed of light. If we had something traveling at the speed of light, it would follow a 45-degree angle between the x and the t axis here, or the ct axis, if you want to get our proper units. If I rotate this in 2 dimensions, again, it's actually rotating in 3 dimensions. If I could draw this as a 4-dimensional diagram, we would get this cone-like surface. Now, all I'm able to show here is x and y. Again, z is there too, but in order to represent time in the vertical, or the speed of light times time in the vertical, I had to leave z out. Okay, so we'll sometimes see these light cones used. You'll hear the term Minkowski diagram sometimes used, and when we talk about things like time-like, okay, the association between A and B are time-like. You'll see that in some of the literature. Without going into too much detail, let's say I keep something stationary, okay? And event A happens at some location, event B then happens at a later time at the same location I haven't moved, okay? We say this is time-like because event A and event B, okay, are just separated by time. They're at the same position, okay? It's a little more complicated. We would also say that if I had event A and B happen within this cone, but at 2 different locations in one frame of reference, okay, it's still time-like. I can still engineer a frame of reference. I can move in such a way that event A and B will appear to occupy the same location, even though they're separated by 2 different times, okay? This is similar to what happened with our boxcar, the whole simultaneity thing, that in our, let's call it our blue frame of reference, clearly A and B happen at 2 different locations at 2 different times. That's fine, okay? In my purple, in my transformed coordinate system, however, now A and B line up in the same position. They're both on the t-axis, or at least the t-prime axis, okay? And in fact, I can put B anywhere inside this cone. I can move forward, I can move backward, which would transform it the other way, and still line A and B up at the same location. This is really cool, okay? Such that everything in this region right here, this volume right here, within this light cone, would be time-like, okay? It doesn't mean that it's going to be at the same location in every frame of reference. In fact, it won't. It can't be. But I can find a frame of reference where I can, align the 2 up such that they occupy the same location. So time-like, okay, they're only separated by time. Okay. Light-like. Again, I feel so clumsy when I try to explain these things. Light-like. Nothing travels at the speed of light except for light. Light doesn't have mass. We'll talk more about that in a little bit later. The best way that I can come up with explaining the connection between A and B, we could have light, propagating through event A. Remember, event A has a position and a time at which it took place in. And then event B, which happens at a different time and location, could also have that same light pass through it. Okay? To get from A to B, you need to travel at the speed of light. We, having mass, would not be able to do that, but certainly a photon of light would be able to move along the cone and therefore is light-like. Okay? I know there's physicists out there who are just cringing by my explanation. Outside this cone, we then say the events are space-like. A and B, okay, they are separated. They are separated by space rather than time. So when something is space-like, okay, I can find a frame of reference. You see this parallel? I can find a frame of reference where I can have them happen at the same time. I can make them simultaneous, okay, but they're going to be at different locations. All right, so space-like, they're separated by space. Time-like, they're separated only by time, or at least I can find a frame of reference which are separated only by time. All right, I bring this up because this is often brought up in the literature when we talk about relativity. We're an introductory course, so we're not gonna get crazy with this stuff, but hopefully in my clumsy way I explained it so it makes a little more sense. Here's something that's really interesting, and again, using these diagrams, I'm not doing this complete justice because I always argue that the twin paradox was more a general relativity thing than a special relativity thing. But we're gonna do our best with this because you need to accelerate in this story. So, oh, by the way, I have to give credit to Paul Hewitt, who does a lot of these drawings. Unfortunately, my credit has shifted off the page here. Paul Hewitt, thank you. But in any case, this is an example where we hypothetically have this, near light speed travel. We're traveling to another system, back to our example of Alpha Centauri, for instance. And in this case, two twins, okay, one happens to be an astronaut, the other one happens to be the observer. Two twins separate when the astronaut goes off to, again, explore some other star system. The rocket returns back to Earth, and the twins are surprised to find out, well, no, if they have the technology to travel near the speed of light, they would have known that this was going to happen. But when the twin returns to Earth, a little bit of a rough landing right there, the astronaut twin is much younger than the twin who stayed behind. And again, this goes to that whole time dilation effect of traveling near the speed of light, where the time runs differently in the two. Well, here's the problem, right? According to this astronaut, as they were leaving, everything that was moving relative to the Earth seems to slow down. Whereas the other twin on Earth saw that, no, in your frame of reference, the spaceship frame of reference, time is slowing down. Okay. How can time run differently in both frames of reference and then the reconnect at the end? Well, let's try to do this with our little space-time diagram, light cones. Now, if you look at this, we see the twin on Earth, at the time which the rocket ship takes off, the twin on Earth is left behind by the astronaut twin. The astronaut twin takes this trajectory, whereas the twin on Earth takes this trajectory. And, your intuition would say, well, wait a minute. It looks like the twin on Earth took a shorter path than the twin who went to Alpha Centauri and back, or whatever, system and back. And therefore, shouldn't the twin in the rocket have aged more? Okay, that's not how it works. First of all, we're cheating, okay? Because the twin in the spacecraft is going to undergo acceleration. Special relativity doesn't do well with acceleration. They're going to accelerate to go faster, and then they're going to have to slow down before they reach the star system. So more acceleration. Then they're going to accelerate in the opposite direction, head back to Earth, okay? And then decelerate as they reach Earth. So there's acceleration going on here, which I argue should be more in the realm of general relativity. You think I'm awkward now? Wait until I try to explain general relativity. But we have to take a look and see how our coordinate systems transform. There's actually 3 different coordinate systems that we're dealing with here. We're dealing with the frame of reference on Earth. We're dealing with the frame of reference as the rocket is heading off to whatever star system it's visiting. And then we have to deal with the spaceship on its return journey heading in the opposite direction. So that's another transformation that's going to take place before it returns to the original frame of reference. So when we look at this, here's what's happening. And I tried my best to superimpose one frame of reference onto the original frame of reference. So this arrow right here represents my x prime, okay? Once I reach speed and I'm moving at a constant rate away from the Earth, and that astronaut twin is heading toward Alpha Centauri. Okay, then after visiting Alpha Centauri, taking lots of pictures, we're returning, we have a new frame. Now we're moving in the opposite direction, okay? Remember, we can switch back and forth, forward or backward here. So when we do the transform, this would correspond to a relative positive V. This would correspond to a relative negative V. So there are 3 frames of reference here. Okay. Now, I tried my best here. I show the time, here we're going right here. This line represents distance. If I go perpendicular to distance, I'm going time. So these are steps in time. Here's a step in time. Here's a step in time. Here's a step in time. And what you notice here is that if I line up this time with the original time, okay, and then I switch my frame of reference, and I line up this with this, okay, I say additional time, there's a huge time gap, all right? Basically, and admittedly, this is a very sketchy, you want to say sketchy? Sketchy way of saying that there's more time that, the astronaut on Earth experiences than the astronaut that goes off into space. But basically, it does show that when you go through these transformations, that time doesn't flow evenly, depending on your motion. And if we were just to go away and never reconnect, it wouldn't be a big deal. But when we do reconnect, we get this so-called twin paradox. It's not really a paradox, but it's a paradox in the sense that we see the flow of time as being constant, and it's really not. It depends on your frame of reference. It's going to get even hairier when we get into general relativity, because with general relativity, anytime you have an accelerating frame of reference, that will also affect the flow of time. And that's not taken into account here. This is purely a special relativity approach to this problem. Okay. All right. So I tried my best. Hopefully I did okay in explaining a little bit of this Lorentz transformation. Really, as an introductory course, we're more interested in do you understand, how to calculate time dilation, for instance, the problem of the muon. Do you know how to do length contraction, which is also associated with that muon being produced at the top of the atmosphere problem? Okay. If you want to delve into this deeper, I have provided links on the Blackboard site so that you may investigate this in more detail with people who do a little better job explaining this. Okay? All right, folks. We'll end it there.